So yeah, I'm going to talk about this very unusual deposit, which is Nolans Bore. It's located, it's about here, not far away from Alice Springs in Northern Territory. And it's pretty much just veins and dikes of apatite. Okay, it's really weird and has a bit of diopside around it. The whole rock, the bulk rock, is about 5% TREO. So if you know, if Ross was talking about stuff that was 0.0 something, now we're talking about 5, and those zones of 5 are actually pretty big. What's even better about it is that it has a very high proportion of neodymium and praseodymium. And this is a rare element pattern of the apatite there. And if you look at most of the deposits, especially in carbonatites, this goes up all the way here. And then it means that the relative proportion of lanthanum and cerium, which are usually cheaper and we don't care about them as much, is higher. And it dilutes the valuable stuff. In this case, you can almost see that the pattern here almost has a maximum at praseodymium and neodymium in some cases, which is what we want for the magnets and the electric motors. So this is why it's so fun. It looks pretty much like this. So here's a bit of core. Have just almost pure green stuff, which is the apatite. And in some cores, you can have in 5 meters of this stuff. 5 meters is pretty amazing. You know, it all has 3, 4, 5% of TREO. It has a bit of diopside around it, not much. And it ranges from centimeters to maybe 1 or 2 meters. And then it's hosted by those granulite fascist rocks, the granites, a bunch of siliceous stuff. And the fingerprint of that is very small, because if you would poke a hole here in the ground and sample only this, you would have absolutely no idea you have this next to it. And unlike other deposits where you have, think porphyry, you have polylytic alteration that extends hundreds of meters and kilometers away. Here, no. Here you just have maybe a meter of diopside and then nothing. So I'll talk a bit about later about how we can find them after all. So it's a beautiful picture of how it looks. So here's the apatite. So this is a bit of core. Here's the apatite, a nice hexagonal crystal just sticking out of it. And this is the diopside. So this is looking just at the contact between the apatite and the diopside. And here's a backstated image from an electron microscope. The apatite is so bright because it is full of earth elements. And it's another image of, so those things are maybe 2 centimeters wide, and you can see that most of the stuff is green apatite here and here. And it has some calcite, a bit of quartz, a bit of allanite, a bit of zeolite, so nothing too amazing. Most of the stuff is in the apatite, and of course we have the diopside just next to it. Also has a bit of halophane, and I'll talk about that in a bit. How do you make this? This is really weird, because if you open any textbook on geology, you don't find dikes of apatite. Dikes or huge veins of apatite should not exist. And when I started to work on it, there were several ideas. You know, people were saying maybe it's fluids coming off an alkaline melt, maybe it's fluids coming off a carbonatite. I was thinking, well, you know, apatite and diopside are rock-forming minerals in carbonatites, and rare earth elements are common in carbonatites. So could it be related to carbonatites? So that was, I think, a legitimate question. The problem is that it is actually not a carbonatite, because as I showed you, most of it is apatite and diopside, and the tiny bit of calcite that is in there isn't actually igneous. It's in late stage, low temperature alteration veins, and calcite is maybe, I don't know, 1-2% of the entire thing. So it's not a carbonatite, but I did wonder whether it's related to a carbonatite. Now, when you look at the mineralization itself, most of it looks like this stuff, okay? This dotted texture that you have in here. So you have the dark gray thing. So those are just earth element pure apatite. And it has full of inclusion. It's full of inclusions of all kinds of rare earth element carbonates, you know, so things like bastnasite, parisite, zincosite, monazites or phosphates, weird silicates, you know, that there's something that's called a statindite. There's something which is some silicate phosphate that doesn't even have a name yet, and I'm wondering whether we can define it as a new mineral. This is important because, you know, when everyone is talking about Nolans Bore as this apatite deposit, but the actual mineralization now is mostly in those secondary alteration minerals, and knowing what the minerals are is kind of important. So here are two patterns of minerals from there, and let's have a look at this statindite. Okay, it's dominated by cerium, which is probably the element that we care about the least. And when we look at, let's say, the contents of neodymium, okay, so down here, we are about 10 to the 5th times chondrite. But if we look at this phosphate, or silicated phosphate, there's almost no cerium, and neodymium is much more. So if we started here at 10 to the 5, this is in log scale. So no, then we have like double or almost triple the amount. So this can make the difference between something that has half a weight percent of neodymium to something that has a weight and a half of neodymium, which is, it makes a lot of difference. So always important to know the mineralogy of your deposit and not just rely on just you know, a blanket statement of here is the TREO. You need to know what it is in terms of minerals. The other thing that we can see here is that the alteration is actually, it's a second stage. It replaces this bigger, nicer apatite. That's big, it's zoned, it's a bit brighter. That is because it has those earth elements inside, actually in the crystal structure of apatite. Those are actually very hard to find in Nolans Bore. I'm showing you a picture, but they're almost not there. Here's another picture of how the things look like. This is something that's called a peel apatite. So there was a review paper on apatites and carbonatites, and they say that almost all of them have apatite that looks like this. They call it peel apatite, and it's something very characteristic of carbonatites. When you look at the composition of the apatites, it plots pretty much in the carbonatite field. So what we care about is the igneous type. So those are the green ones, and it plots either in the CB field, which is a carbonatite field, or in the extension, if you include all other apatites that are earth elements rich from carbonatites. Okay, I was also telling you that other than the apatite, we have diopside and a bit of halophane. So halophane is something very typical of alteration around carbonatites. Diopside, it's a common mineral everywhere, but not when it looks like this. So those are the earth element patterns of the diopside, very typical of carbonatites. You know, so many things about it just look like it's a carbonatite. Okay, except the problem that there are no carbonates there. So it's a bit hard to think about what it actually is. Fortunately, at ANU, we have an experimental lab. And if you have an idea, you can just go and test it. So the feeling I was getting is that whatever made Nolans Bore made it by reaction with the host silicate rock. So I took a silicate rock, I took a carbonatite, I put some earth elements and phosphate in it, and I put them in a capsule. So those things are maybe 1 centimeter long and maybe 4 mil wide. And I ran them at 6 kilobars and 650 to 900 degrees to melt them. And you can see that you have all of those blobs of carbonatite and liquid carbonatite going up, interacting with the silicate rock, and all kinds of shapes and colors in here, and also here a bit harder to see. And those things are all kinds of different minerals that crystallize during the reaction. And you might guess the minerals that formed were diopside and rare element rich apatite. Now, this is a closed system. All of this stuff is stuck in a capsule, but imagine being in an open system, in a shear zone or a vein in the earth. You can have a carbonatite liquid going from here, going left, reacting with the silicate rock, leaving behind this solid residue, which would be diopside and apatite in our case, and then it goes elsewhere, leaving behind no obvious hint that you actually had the carbonatite. And we only know that because from the experiments, we could make it. So it's consistent with what we see in nature, and the chemistry and textures that we see in the residue, in the cumulate if you want, are exactly what you will see in proper carbonatites that actually have the carbonates in them. So I made this kind of model of how it formed. So you start by having some kind of shear zone in a silicate rock. Then you have intrusion of carbonatite melt. This carbonatite melt is crystallizing diopside because it's reacting with the silicate rock. And it's also crystallizing apatites. Now, those apatites are crystallizing from a carbonatite melt, and you can think of, I don't know, a gaboic melt that eventually would have plage in CPX, but it can also crystallize olivine. Okay, so the fact that we don't have carbonates doesn't necessarily mean that it was not a carbonatite melt that made the apatite. It gets a bit bigger, and all of those small apatites end up making those peel-type apatites. You do have a bit of titanite and halophane depending on what you have in the wall rock, and then eventually the carbonatite melt is gone. You're left with some kind of low-temperature fluid that then crystallizes into zeolites and hydrothermal apatite and allanite and barite and all kinds of other things we have in there, also a bit of calcite. One of the important things to notice is that you don't always get mineralization. Very often you have those very tiny small veins with hardly any apatite in them, but they're full of diopside that looks exactly like what we have in the big ones. And that's important. I'll talk a bit about that in a bit. Also did a bit of isotopes with the help of Vicky Bennett. Very imprecise, about 10% uncertainty, which is a lot, but it is within error of the much more precise age we got from Dave Houston and the team at GA. The interesting thing here is that we got a very constrained range of the initial igneous stuff in terms of epsilon neodymium, which is about -4 to -5, and the strontium isotope ratios, which is about 0.704-ish. And when you look at the whole rock, as I said, it was altered, it goes up. So there's some kind of exchange with the host silicate rocks, which are way over there, maybe 7.1 something. And if we got some radiogenic strontium into Nolans Bore, we also got some non-radiogenic strontium into the wall rock. So this is something that we could use as an exploration guide. You can think of, if you find those things in any granulite fascist rock, and I'm pretty sure that most of you have seen many, many diopside or pyroxene veins in granulite fascist rocks, and you didn't really care about it. But maybe it's a good idea to have a closer look. Have a look at the strontium isotope ratio, have a look at the reference patterns of the diopside. Do you see a carbonatitic signature? Do you see a mantle-like signature? And then if the answer is yes, maybe, you can have a Nolans Bore nearby, because, if there's one, I'm pretty sure there are more. Yeah, finding it is a bit hard because this is where it is. It's just, in the middle of the Northern Territory. It's bang on in the center of Australia, and it's here. It's this area, and even though, it's full of outcrop around it, that's Reynolds Range, full of beautiful outcrops of pretty much everything. Nolans Bore just happened to be in the tiny bit that is undercover. And trying to find something like that would be, like playing Battleship and trying to find the boat that is only 1 square large. But there are hints. So, for example, those veins that you can think, you can find, I think Nolans Bore was initially found because of the airborne radiometric surveys found some kind of anomaly. So this is another thing. Now, in terms of the overall tectonics, so this is the model that Dave Houston did in his paper, in their paper. And I'd like to add a few more things here. So you have where it's actually coming from. So it's coming from the mantle. And actually go to the next slide, where it shows that you had decompression-related partial melting of an enriched mantle, okay? And this made a Nolans Bore. In their model, you had fluids coming from an alkaline melt. In my model, it's a carbonatite throughout the entire thing, but that is less important now. The interesting thing is what has enriched the mantle, and then you have a subduction zone. Now, one idea is that that subduction zone was coming from the Mount Isa region. And the Mount Isa region is very famous for phosphorites. So that could be the thing. And if we would try to put some kind of geography here, so the Northern Territory would be here, the border with Queensland is around here. So there could still be a bit of Nolans Bore type enriched mantle underneath. And because the western part of Queensland looks pretty much, I mean, it's high grade crustal granulites and stuff like that. So this looks like something where you could find an Nolans Bore. So, you know, if you can find those diopside veins that look kind of carbonatitic, so maybe there's a Nolans Bore nearby. Just a bit of summary here. I think I'm out of time. So I'll let you have a look at it, and that is all I have to say. Thank you.
Thank you so much, Michael. Does anybody have any questions for Michael? I'll just have a quick check of the chat. I think you've bamboozled them all, Michael. All right, well, thank you. And if you do think of anything you'd like to ask Michael, then stick around for the drinks afterwards. Now, oh, Lucy Chapman has a question. Go ahead, quick, awesome. Lucy. Put it in the Q&A and maybe Michael can answer it during the next talk.